Homework 7, problem 5. Given an infinite cylinder with a locked-in magnetization that is proportional to the distance from the center of the cylinder and points along the axis of the cylinder, find the magnetic field everywhere. To do this, we're going to do this as a two-step process. We're first going to find the bound currents, so the bound volume and bound surface currents. And then we are going to use Ampere's law with those currents to find the magnetic field. So step 1 is just find the current, and so that is the bound surface current is the magnetization vector across the surface, and this is evaluated at the surface. So at the surface, this is K if we define this as distance A, right? This will be K times A. And then we're going to get Z hat cross S hat, which we know is in positive phi hat direction. So the bound surface current is Ka in the phi hat direction. J would be the bound volume current, is the curl of the magnetization field. Now to do this, we have to look up what the curl in cylindrical coordinates is. There are only two terms that contain work on the Z component, so I just looked this up in the front of Griffiths. They have the list for curl and cylindrical coordinates. The two terms that act on the Z coordinate are 1 over S times partial with respect to phi of the Z component M sub Z. This is in the S hat direction, and then minus partial with respect to S M sub Z in the phi hat direction. Now, one of the things we know is this is independent of phi, so this is 0, and so left over, this will be the bound volume current is going to be the partial derivative of M sub Z, which is just Ks with respect to S, so this is just K. So this is minus K times phi hat. And so now we have the surface and the volume currents. It is kind of interesting that they're going in different directions. The volume current is a uniform volume current that is going around in this direction, right? And the surface current is a larger current going around in the opposite direction. So it is kind of interesting that we see something like that. In any case, now we want to use Ampere's law to find the magnetic field. Ampere's law, we're going to use our usual Amperian loop for cylindrical or solenoidal system like this. The Amperian loop is the one I've drawn right here, and so here our N hat is actually in the minus phi hat direction, right? If we go down here and up here, we might as well label the two distances, and so label the distance to the inner loop S, and we can of course label the distance to the outer loop B, or whatever we want it. The important thing to note is we can do fairly quick analysis. If we take this loop and we extend it through the other side, then we go down here, up here, and the magnetic, the current, because we have all current going in one side has to come out the other, the total current going through this whole loop is 0, so we'll have 0 contribution from these two legs. And so we just know that the magnetic field outside of this infinite cylinder is 0. And so writing down Ampere's law for this system, Ampere's law is the integral over a closed loop dl dot 1 over mu naught times magnetic field is equal to, of course it's equal to the current enclosed, and so this is integral d2x n hat dot j. And so here we're going to use the J bound and the K bound. So this is the current enclosed. So this is the I enclosed. Here we should note we're going to use symmetry to argue that B is only in the Z hat direction. It is not in the S hat or phi hat direction. Because of that, we only get contributions from this loop and this loop. Furthermore, we've argued that the contribution from that loop is 0. And so since this doesn't depend upon Z, it will only depend upon S, we are going to say that this line integral just gives the length of that line, so define the length of this line as L. So this is L times 1 over mu naught. It's in the minus direction, right? So minus L times 1 over mu naught times the b in the z direction as a function of s. This is going to equal the current enclosed. The current enclosed, remember this is in the minus, the normal to the surface is the minus phi hat, so we're going to get a minus from here. We have minus L, that's the length, and then times Ka, and so this is the from the surface current, because the surface current is enclosed, is that part right there. And then we're going to get in the positive direction, right, plus the stuff that goes through here. So I have to multiply this volume current, which is minus K, times this area. This area is A times S. So this will be L times K, and then A minus S. Right? And so canceling everything out, right? The KA's cancel, and we get that this is minus L times K times S. The end result of this is that the magnetic field, which is a function of S, is going to be positive mu naught K S. And so the magnetic field, generalizing this and back into a vector field, magnetic field is a function of R, is mu naught K S in the z hat direction. And that is the magnetic field for an infinite cylinder with locked-in magnetization.